Generative adversarial networks, also known as GANs, have marked a major breakthrough in the ability of AI to generate realistic 2D images of people and objects, and ushered in the possibility of true AI creativity and realism. Nevertheless, generating 3D objects has remained a challenge for our current neural network models due to the difficulty of representing 3D data in the neural network architecture. Enter BlankCompose, a novel 3D-shaped generative model that brings the power of GANs into the 3D world. BlankCompose combines high-fidelity expressivity, controllability, and embedded data analysis. We collected a high-quality dataset consisting of over 5,000 diverse car models covering 70 years of automotive history. The 3D models were then fully labeled with over 20 relevant properties, including design concepts, properties focused on the market, on the customer, or other engineering properties. BlankCompose leverages our proprietary 3D representation and matching GAN architecture to allow for a fast and effective processing of 3D data, combined with high-level labels to generate controllable 3D designs. The encoder network converts a random seed into a compact latent vector that represents a unique car model. The decoder network transforms this latent vector into a full 3D car model. We can view this latent vector as a point in a high-dimensional latent space that covers all possible cars. Let's begin by demonstrating the quality of a generated 3D car model. Note the high resolution and level of detail on elements such as window frames and front grille. Next, we see the random generation of cars in our latent space. Note that this demo is running in real time and the model can generate dozens of diverse and high-quality car designs per second. Now let's look at ways of harvesting the power of our generative model in structured latent space. The first feature locates real car models inside our car latent space. For that, we use a search algorithm to find the closest match for the target car model. The decoder then takes the predicted latent space location and generates a 3D model. We start by choosing a model, such as a coupe BMW Z4M. We see that the decoder is able to accurately approximate the BMW Z4 shape from only 512 numbers. Having 3D models represented as a point in a structured space allows us to explore multiple interesting vector operations and transformations on the designs without leaving the manifold space of realistic models. The simplest operation is to blend between two predefined points in the latent space to generate realistic hybrid models. We can start by choosing a car from our list of cars and fix that as a target point. We then choose another car and fix this as our source. Now as we move the slider, we explore the space of possible cars between the two. We created two intuitive editing tools that allow for high-level control. We can look for areas of the latent space where most car models of a specific type are located and split the latent space accordingly. This now gives us navigation direction to bring any generated model closer or further from its specific car type. The same can be done for any label we have in our database. Let's start by randomly generating a car. We open our Tuning by Attribute menu to find multiple properties that we can directly edit, like car type, make, and other numerical properties like model year, wheelbase, and fuel consumption. Take an average sedan. We can turn it slowly into an SUV, then add some sportiness but increase its coupe factor. If we want to edit the rear of the car, we can increase the hatchback factor, then add some Ferrari DNA into the mix, and we get a very interesting hybrid car. Now let's take this car back in time and see how it would have looked a few decades ago. But what if we don't want to use our own labels to define the latent space? Well, we can also use a data analysis algorithm called principal component analysis to examine the data distribution in our learned latent space and extract the most expressive directions that fit our data without requiring any labels. The names given to each slide are our own rough descriptions and are not directly correlated to a predefined label or goal. Another useful feature enabled by our data-driven approach to 3D design is using our latent space as a data analysis tool. By looking at the location of a 3D design in our latent space, we can extract its nearest neighbors from our real car dataset, giving the designer an objective measure of similarity to previous designs. Here we can see a list of real cars closest to the current car model in the latent space, sorted by distance. Clicking on one of them, we can further explore its nearest neighbours. The flexible combination of features and interactivity enable vast potential applications for 3D GANs across design, strategy and marketing, as well as education. As a design tool, Blank Compose can be easily integrated into existing workflows. The generated car can be directly exported for further post-processing in any professional tool. If you're interested in learning more about the potential of Blank Compose, please visit our website and get in touch.